Welcome everybody. My name is Neil McRae. I look after network architecture. I am actually from the north, but this is about as far north as I like to go, especially when the weather's like this. But big thanks to Trev for hosting us. I'm going to talk about some of the work we've been doing in optical transmission systems, and in particular how we are integrating more of our transmission systems with our IP network. I'm going to kick off with a quick overview of BT's network architecture. It's split into a number of usual domains. From optical transmission, it drives our fibre to our packet core network, our service switching network, which is our BRASs and our VPN devices, our voice platforms, content and applications, so our TV platforms. And then the box to the left is all kind of OpenReach's domain, EAD, FTTP, FTTC, ADSL, services that we offer either through OpenReach or through wholesale. We're really focused on simplifying our network. BT's network is probably the most complex thing I've ever experienced in my life. There's a lot of legacy. You can visit a BT exchange and it feels like you're in a TARDIS where you can visit the 80s, the 90s and last decade. So there's a lot of legacy and a lot of challenges in maintaining the platforms and getting value for money out of them. What I'm going to talk about today is specifically how we are integrating our optical platform with our IP network at the core level and how we're using 100 gig alien wavelength technology to do that. Just a bit more about our vision. We talk about service ingress points, which is where you kind of plug into BT. These you buy from a BT MFU, BT Retail, BT Wholesale, OpenReach or Global Services. And we offer very different types of service, DSL, voice, trading platforms, but they all kind of come into what we call a service ingress point. And one of the core strategies we have is to reduce the number of service ingress points. Some of you, if you're a wholesale customer, you may be taking part in a trial that we're doing on a platform called MSE, Multi-Service Edge, which I might come and talk about at the next meeting, which is our kind of move to distribute network access into a much wider set of locations to do two things. One, to reduce the complexity of the network, but two, also reduce the cost of it. And that's dependent on what I'm going to talk about today, which is how we get more out of the optical platform that we've got. So here's a quick agenda. I'm going to give a quick overview of Coherent Optical Technology, which is a kind of a 2-year-old technology that has helped us move from 10 gig wavelengths into 40 gig and 100 gig wavelengths. And then I'll talk about IP over DWDM and some of a trial that we worked with Cisco, Ciena and Huawei over the last couple of months. So what is Coherent Technology? Coherent Technology is all about digital signal processing. If you imagine a fibre today, that fibre kind of blinks really quickly. That's how it works. And the longer you make that fibre, the harder it is to detect that blink. What Coherent Technology does is it measures a number of different parameters across the fibre using a digital signal processor to enable you to detect the blink better. And that's in very simple terms. I could do 4 hours on Coherent easily and confuse the hell out of you because it confuses the hell out of me. It's a very high-end mathematical signal processing technology. And actually, I was at a fabrication plant where they make DSPs. The DSPs for 100 gig technology is the most powerful computing element that you can buy now. There's nothing that comes near because the volume of computation that you need far exceeds anything else. So this is very specialized silicon. This is actually a Ciena slide that I quite liked that kind of talks to what the differences are between kind of former mode of operation and the future mode of operation. One of the big challenges, I mentioned this earlier, one of the big challenges of optical networking is loss, i.e. you shine a light and how far does that light go? And it's driven by a number of things. One, the length. Two, the power of the laser or the LED that you're using, but also the quality of the fibre and the number of joins that you make in the fibre. Every time you connect one fibre to another, you have loss. As you scale or drive the light, sorry, not drive the light faster, but as you try and drive more bandwidth, you introduce two types of what we call loss. One is chromatic dispersion, and that's effectively, a simple way of looking at that is, you may have remembered in physics when you were at school, if you shined a torch on a prism, a wavelength of white light would transform into many different colours. Those many different colours operate at different speeds. So if you have a blue wavelength, it's liable to arrive slightly before the red wavelength. And the further you go, the worse that problem becomes. So if you're using multiple wavelengths, all your traffic starts to arrive out of order. The other one, and actually, chromatic dispersion is linear, so you can kind of predict it quite easily. The other big issue that we face is called polarization mode dispersion. And this is a really tough nut to crack because, in effect, when you shine light on a fibre, there's two planes of operation. There's a horizontal plane and there's a vertical plane. And there's no way to control those planes in the fibre. And what tends to happen is they get mixed up and it smears the signal, which basically means it doesn't work. PMD has really been a barrier for us getting beyond 10 gig at any sort of useful distance. And there's a number of technologies that have solved that problem, the biggest of which is Coherent Technology, which just allows us to look for the specific channels we want to address in a fibre at a specific wavelength. That's a kind of a very high-level view of it. There are other ways of dealing with PMD and chromatic dispersion, which is kind of replace all the fibre with really straight or really brand-new fibre, add a bunch of filters to filter out some of the bad information, but ultimately they cost a fortune and they're not really scalable. And if you think about it, you know, we're building cable systems that are 400 or 500 gig, you know, a couple of cable systems that are going to be terabit capable. So in order to get the maximum out of those cable systems, we need to be able to run the wavelengths at as fast a speed as we possibly can. The other thing driving this, of course, is all the traffic we use in internet land sits on an optical platform. And the really important thing about optical networking that's overlooked is your first cost that you have in electronics is the optical platform. And if you get that platform wrong, it doesn't matter how cheap you make the top bit, because your bottom bit's so out of kilter, you'll just never make it in terms of high bandwidth services. So getting optical platform really right is super important. And you'll see if you get, you know, this is quite a specialised area, but if you look at some of the technological advances in networking, many of them are at the optical layer. Few of them, actually, in my mind, are at the IP layer. Yeah, we've got a load of new protocols and standards, but actually, in terms of silicon development, in terms of laser development, in terms of manufacturing process, opticals where a lot of the real big leaps have been made. And if you Google any of this stuff, there's a load of stuff on YouTube. There's a guy called Dr. Fiber that can take you through a load of detail on some of these issues. So Coherent gives us the ability to use our existing assets of fiber and of network and drive them to 40 gig and 100 gig and roughly run about 80 to 100 wavelengths. So 100 gig wavelength and having 80 of them. That sounds like a useful amount of bandwidth to me. What we have trialled in BT is to take that one step forward. So that loads of operators are using Coherent. They have been for some time. If you buy a 10 gig wavelength of a kind of a semi-large to super large operator, the chances are they're using Coherent to deliver it in a 10 gig wavelength in a 100 gig container. And Coherent Technology allows them to sell lots of 10 gig wavelengths. Whereas historically, the maximum you could probably sell was maybe 50 or 60, depending on the fibre and the distance you wanted to go. So Coherent Technology is well deployed. We have it deployed at BT, at Cable and Wireless, where I was there before. They were deploying it as I left. It's a tried and tested technology, and it's going to enable us to get to 400 gig wavelengths and 1 terabit wavelengths. So the next part of this presentation is just to talk about how we build networks today with the optical platform and how we see that evolving. So today you have a router, or a router if you're from my part of the world. You have an optical platform, a multiplexer from Ciena, from Huawei, or from Alcatel-Lucent, and there's a couple other littler guys in this space. ADVA do a lot in this space as well. And you have an optic and a receiver per platform. So your router has an optical transmitter called a GBIC or a CFP or an SFP. That connects to the terminal of a DWDM system, which also has the same thing. So just to have one link, you kind of need a bunch of optics, and optics are actually quite expensive. It's a kind of a chemical process to grow some of these optics, and by far one of the biggest scaling items from a cost point of view in the network are how many optics you've got there. Where we're moving to is actually, if I've got an optic in my router, why do I need anything in my DWDM system? Why can't I just turn the power up and run it on the platform? And this is a technology called alien wavelengths. In the ITU, it's called black link, but it's the same thing. And this is effectively a technology that allows you to inject light into a fiber, but from a system that's alien to the optical network. Hence the term alien wavelength. What's the benefit of the approach? I think I've talked about that a little bit. I mean, the big benefit is you need less transponders, and that saves you a ton of money. You also are able to integrate the optical network and the errors and management of it into the IP layer in a much more granular way than you have been able to before. I don't know how many of you dealt with a situation where something was working on an optical box, or either a GBIC or some sort of optical connector, and then tomorrow it stops working and nothing's changed. And trying to detect that is actually very, very difficult. It's a very small margin between an optical transceiver working and it not. And we've had previous talks on how to clean fibers and all sorts of stuff to reduce the nature of those sort of failures. With this, at the IP layer, you can actually detect, this fiber is degrading, maybe I want to move off of it. And you're able to get a lot more telemetry from the optic of the router that typically you would have had to phone some other guy in the network operations center to get that sort of measurement from. Why is that important? Today, more and more IP networks are carrying what I call life-critical traffic, phone lines, TV services, video games. You know, everyone's wandering about with an iPhone or some sort of smartphone, and when it doesn't work, we all kind of have a bit of a paddy because, oh, why isn't it working? All of that stuff sits on this, and when we have network outages, it doesn't work, and people get frustrated and upset and phone the help desk and complain. So this really enables us to improve the reliability of the core network, and it's really important here. When the core network has a problem, everybody has a bad day. You know, it's not just your DSL line, it's everyone's DSL line. So it's really important that we improve the reliability of there. So we ran a trial with Cisco, and we're working with Ciena and Huawei, who supply the DWDM platform for BT. And we wanted to run a trial of this black link, so we set up a network, and we built some dedicated components, and we ran a number of trials and tests. There's a couple of reasons why we want to do this. We want to have as many suppliers in the optical market as possible because it reduces the price, and when you're selling DSL for 10 quid a month, anything you can do to reduce the price is a good thing. So more competition means better pricing, also means more innovation in terms of how they make optic devices, how they sell them, how they roll them out. That's one big driver for us. The other big driver for us, by understanding how it works, we can influence the standards on it and make sure, you know, from our own point of view, that things are important to us, we can help influence. And that, I think when you've done a trial and you know how it works, it's always easier to influence a standard or an operational model. And of course, it gives us a great talk to have at UKNOF. So this is a very high-level overview of what we did. So on wavelength 1, we have our Cisco CRS3. with Cisco's, this was a prototype card, an IPO DWDM 100 gig card. We also had a bunch of other routers on these other wavelengths, but using traditional CFP to the DWDM transponder, so the traditional way that we use a wavelength and a transponder. Vendor 1 was on a span Sienna of 410 kilometers. Vendor 2, Huawei, was on 359, but we also actually decided to connect them all together, which gave us a reach of 769 kilometers. And clearly in the UK, which is a big market for BT, obviously, 769 kilometers is, it's way more than we need from a regeneration or an optical to electrical point of view. We mixed a number of different wavelengths, 100 gig and also 40G. And also, one thing that's really important, BT's fibre has been in the ground for quite a long time. It's not the newest or the best fibre that you can buy. So typically, when you're building fibre today, you put DCM, which is dispensation compensation modules, and they usually look like either a box or a kind of a thicker bit of fibre at the start of the span. And most networks today in the UK, there are very few that have that. So if we have to go and deploy that technology, in effect, it's a filter that filters out noise. It adds to the cost. So making sure this worked with our fibre in the ground was quite important. This is the network that we built. So at Astral Park in Ipswich and BT Tower, and we routed it. And we routed it through a number of our exchanges. The red is Sienna, I believe. Let me remember that. Yes, and Colchester. Yes, and the green line. So ignore the bit at the top. The green part is our Huawei test platform, and in effect we have a couple of racks worth of equipment in that Astral Park, and at BT Tower we just installed a loop because we've effectively built a big line back to the end and B end, but it shows that this is run over field deployed fibre. So what's really important here is what is the signal to noise ratio. And the signal to noise ratio here was no worse than what we see in a regular system. It was in the margins. That tells us two things. One, Cisco's optics in their routing are as good as the vendors that produce optical equipment. And that was quite important because it's not a field that someone like Cisco's historically been in, although they have bought a lot of companies recently. Two, the other test we did was to see if it would work with. So this figure 1 shows the 100G wavelength. That spike is that wavelength. Figure 2 shows us using some other native 100 gigs on the platform and a couple of 40 gigs just thrown in for good measure. The pulse in the middle of that diagram is the alien wavelength. So from this, we now know that we can run an alien wavelength over existing platform and it won't have a negative impact on any other traffic. I won't even try to fake that I know what this means, but in effect, for me the important graph is the bottom graph. Oops, sorry. And what it shows is that over time, the signal-to-noise ratio and the error rate that we get is consistent with what we already see in the network. So it's no worse. The graphs, the constellation graphs, if you're a kind of optical nut, this kind of gets you really excited. What you're looking for is a nice kind of circular kind of path there. And what we see for these constellations is, again, and actually I probably should have put one up, but they're very consistent with what we see in the regular network. So in effect, there's nothing wacky going on with the wavelengths. There's nothing wacky going on with signal to noise ratio. It's working how we think it should work. So I've kind of covered this, but it works. It works actually a lot better than we first expected. We expected many more issues on this. We also made it work over multiple vendors, and in the optical space, making one vendor work with another, despite there being a lot of standards, actually the way DSPs work, none of them are the same. You try and plug a Coherent end from a Sienna box into a coherent end from a Huawei box. If it works, it's a miracle. And the benefits for this, we got to 769 kilometers, error-free, and it shows us that we can bypass and create aliens from our IP network and reduce the cost and also the time to build our network. There's a few other benefits. This takes up a lot less space. It uses a lot less power. And many people might know this, but BT is probably one of the, if not the top 10 user of power. And you may also notice that there's a lot of price increases on energy and a lot of regulation of the price of energy. So we have a big focus on taking costs out of energy. So this is vitally important for us. The other challenge we have in BT is space. We've been installing boxes for 100 years, and we're really good at putting boxes in. We're pretty terrible at taking boxes out. So, anything we can do to reduce the size of the footprint of the network, both in energy and in real space terms, is a big pro for us. Many of you will say, "Oh, what optics did you use?" Because surely we've got all these great new optics coming out next year that are going to be far, far cheaper. Actually, if the optics were free, this still is a cheaper solution than the traditional method. So next year we'll see many more kind of 10 by 10 based optics, both at single mode and multi-mode. That will be a lot cheaper. In fact, some platforms have launched it already. They'll be a lot cheaper, and it helps bring the cost down, and we like that, but it's still not as good as this solution. So we absolutely believe that there's a big cost reduction and simplification of going down this path, and probably next year we'll start to put this into production in the 21C network. So I've kind of covered this, but literally, 555 watts doesn't sound a lot, but when you multiply that by a lot of wavelengths, it becomes pretty significant. We think this will take about 2.5 million quid's worth of energy out of our network. Sounds like it's worth it to me. So some challenges. So the first big challenge is the router manufacturers aren't used to making optical components, so the cards look pretty ugly. Unfortunately, I couldn't show a picture of the card because it's Cisco's. It was a prototype, but they take up big parts of the motherboard. Again, we've seen kind of pictures and examples of how that's going to get better. My expectation, we will see between 4 and 8 ports on a line card being able to do that, especially in the next generation platforms, PTX, 7950, and Cisco's new box that they're working on right now. Also, there's another way of doing this, which Juniper do today, which is you can kind of have an optical shelf that sits on top of the router to take a lot of those components out. The other big issue is obviously how do you really manage this? Because you've typically got a bunch of optical guys and a bunch of IP guys, so there's all the kind of process and knowledge transfer in order to make this workable in the real world terms. And we've started to move in BT to bring those teams together. There's also a draft work going on in IETF and ITU. There's the guys in Deutsche Telekom came up with the management framework, which is a great document. And I think there's one other challenge, one other worry that we have with this is what happens if you have a device that behaves badly and starts kind of flooding the waves, your kind of neighbouring waves with a lot of noise. That's one of the reasons why we think that this is kind of a solution that we can use as long as we own all the optic domain inside it, so we can manage it. I know that there's trials going on in I think it's in Tokyo, where they're looking at offering alien wavelengths as a service. I think that's far from ready in terms of really being able to offer that as a service. It'd be kind of like dark fiber or a dark wavelength would be one way of looking at it. And then we need to do more in the IP space, particularly the vendors, to be able to leverage the data we get from the optical network to use it more effectively. So when we start to see high bit errors, if you think about how much data is transported in 1 second on a 100 gig link, if you have a 1 second outage, just do the math. That's a big lot of data you've just binned. So it's really important that you're able to recognize, bit errors increasing and act on them very quickly. It's substantially important. I mean, that could be someone's DSL for a night. That's how big it is. We did a press release, and that's it. Any questions? These are some of the people that are involved. There's a big team involved. Big thanks to Cisco, Ciena, and Huawei. Open up for questions.
Hi. Can you tell? Sorry, it's Allied Morris.
Hi.
Can you tell me how you tune the output of the line card to match the grid on the DWDM? Or do you have to stock 100 line cards?
They're tunable lasers. Yes. You just say, I want to use this wavelength, enter.
But one of the advantages of a traditional DWDM system is that you can move an input wavelength onto a different grid space if you need to for optical routing or
use a
recovery.
ROADM. Yeah. So
that moves into the router now.
Well, you wouldn't. You're not actually transporting the wavelength through the router. It's still a terminal device. So you wouldn't need. So, in effect, the transponder of the router is part of the optical platform now, and you manage it as such. So if you need to route that to a specific wavelength, then you do that at the kind of management layer of the whole DWDM network. But it's the same component. They're tunable lasers. If you need to kind of drop out, then you're still using the ROADM to do that in the DWDM network to kind of break it out of the rest of the wavelength paths. But that's there today. It's not a new thing.
It kind of does integrate more the role of the carrier with the optical carrier with the routing carrier. So the
absolutely
IP things are blurred.
Yeah. So and that's one of the key challenges is. Let's be honest, Ciena and Huawei and the guys that make optical kit don't really want us to do this because we're going to buy less stuff from them and more stuff from the other guy, right? So how that works moving forward is something that's of real importance. And what you might have is there's a term called a slip where you kind of lose the frame of the network, and it's typically caused by laser sort of issues. If that was to happen, then you could take down a load of other wavelengths at either side of you. So there's ways to manage that, either by putting a guard band in, like we do with GSM today, so that the wavelength, if it does flow over, you've got a bit of space to do it. But that's some of the other testing what we need to do, and that's one of the reasons why I think owning the whole kind of light wavelength scheme, you can't really have one guy doing it over here and another guy doing it over here. That just won't work because it is literally you've now combined it.
Yeah, thanks.
Andy.
Thank you. I really enjoyed that. Where we have optical systems... Sorry? Oh, my name's Andy Davidson from 2Connect. Where we have...
I know who he is.
Where we have... today we have an optical and IP split because it wasn't possible to buy such optics that could do the alien presentation all the way through at the time we made the decisions, etc., etc., etc. And it got me thinking about times it would be ideal to have IP in places we just have optical equipment today. And was that a big driver for BT? Did you already have IP in all these places where you can today with this design?
Yeah, this been predominantly focused for deployment in our UK network. There are our global network just. It's a VPN network. It just doesn't have the bandwidth demand where this is going to make a huge amount of benefit. It's an interesting challenge, and we've done a lot of work on this recently, which is how big does the network need to be, and how many POPs do you need to have, and what is the kind of the ratio between number of POPs and the cost to run it. And we've done a huge amount of work on that recently as part of this, and a couple of other things we're doing. There is not a one size fits all. In my view, but everywhere where we would be deploying this, there's typically already a core router and a DWDM system. And actually, when I joined BT, they're about to roll out a new platform that wasn't aligned, and I stopped it and said, no, router in this cabinet, DWDM system right next to it, because what you don't want to do is have the DWDM system down there, which makes it harder to do this sort of thing.
Okay, thank you, Neil.